Yeah, maybe we can wait for a minute.
Okay.
I think there's still students coming.
Yes. Mm. Okay. Uh, let me start now. Okay. Good day, everyone. Welcome to our first 3-in-1 online Zoom session in text mining class. My name is Putra Pandodikara. Today, I'm serving as the moderator and as the host. Today, we are honored to have with us Prof. Richard Song Han Sai from the National Central University and Academia Sinica, Taiwan. Okay, how should I address you? Prof. Sai, is it okay? Or Prof. Richard?
Yeah, thank you for your introduction. Yeah,
Okay.
so may I begin my talk or?
Maybe I can introduce briefly about you first. Is it okay?
Okay.
Okay, jadi Prof. Sai received his PhD degree in computer science and information engineering from National Taiwan University, Taiwan, and he is currently a professor of computer science and information engineering with National Central University. He is also a researcher with the Center for Geographic Information Science and the Research Center for Humanities and Social Sciences Academia Sinica, Taiwan. His primary research interests include natural language processing, deep learning, dialogue system, cross-lingual information access, sentiment analysis, and digital humanities. This is the CV that I got from 2021. I hope it's still relevant until now. Okay, Prof. Sai is a distinguished expert in his field, will be sharing his valuable insight on intriguing subject of word embedding as we navigate through this virtual learning journey. Let's unravel the complexity of language and computation together. Please join me in giving a warm virtual welcome to Prof. Sai. And now, without further ado, the screen and time are yours. Okay.
Okay, so I think I can begin my talk. Okay, should I share my screen?
Yes.
Okay. Um,
Is there any difficulty, Prof. Sai?
Yes, I'm switching my screen. Sorry about that. I'm setting up my screen because seems that I cannot use my uh, double screen. So sorry, I encountered some difficulties in sharing my screen. So um,
Do you need help, Prof? Maybe I can present the
no,
slides.
no, no, just wait for a moment. Yeah, yeah, because I cannot see my screen in this screen. So um, so maybe I need to enter the chat room again. Sorry. Can you see my screen?
Yes.
Okay, sorry about the late. And
It's okay.
hello everyone. Hello, friends and students from Indonesia. I'm very glad to be invited to be the speaker of the visiting professor and the practitioner lecturer 3-in-1 text mining lecture. Yeah, so today I'm going to give a talk entitled Word-to-Vec Crafting Word Representations. And this is very important and the fundamental of learning how to do text mining in the deep learning world. Yeah, because the first lesson to process text is how to representing a word in a vector space. Okay. Okay. So in machine learning, the fundamental data format is a vector. So how can we convert word into a vector representation is very important. It influences the following processing. So let us think the most straightforward approach is to assign each word its own unique dimension. So in this method, for a specific word's vector, only its designated dimension has a value of 1, while other dimensions are set to 0. This is known as the one-hot representation. So only the word's corresponding dimension is 1, and the remaining dimensions are 0. A major issue of one-hot representation is that its high dimensionality for large vocabularies. This not only increases computational costs, but also means all word vectors are equidistant, failing to capture semantic relationships. So if we want to put this large vocabulary into deep learning network, for example, to prepare weight matrix. So one side is the number of words, and the other side is the number of neurons. So we have like m times n ways to be tuned. That is very huge number. So another approach to word representation is distributional semantics. This principle posits that the meaning of a word can be understood by examining its context. Essentially, if you know the appropriate and inappropriate context in which to use a word, you grasp its meaning. This understanding forms the core of distributional semantics. To understand the meaning of a word banking, you can analyze its usage across a vast amount of text. So by extracting sentences where banking appears, such as governmental debt problems turning into banking crises as happened in 2009, you get a sense of the context in which banking is used. Instead of the long one-hot vectors, we will use a shorter, dense numeric vectors where every number isn't 0. So for a word like banking, its meaning spreads across these vectors' dimensions. So we can see in our right-hand side, we show the real vector for banking. We can see that no values are 0. So for simplicity, I'm showing a vector with just 9 dimensions here, but in real-world applications, you'd often see at least 50. And what is about a common size? It's around 300 dimensions. Okay, so next, we are going to introduce the impactful word vector algorithms, word2vect. So here's the essence of this algorithm. We start with a large text corpus and assign vectors to each word in a fixed vocabulary, initially with random values. For each word in the text, we consider its context, aiming to make the center words vector predict the surrounding words effectively. So after a billion iterations, a transformation occurs, resulting in a word vector space. This space captures meaningful word representations, aligning with their intended meanings. So let's take an example here. Problems turning into banking crisis us. Our focus is on understanding the word into. We aim to ensure that its representation can accurately predict the words that typically accompany it in the context, thereby capturing its meaning. We'll make predictions based on this word's context and continuously refine the vector representations of words to improve our predictive accuracy. So after into, we move on to the next word, banking. Our aim is to understand its meaning by predicting its common context, like turning into crisis us. We predict the words around banking and repeat the process for each word, refining our understanding as we go. So then we can design the word2vect object function. Imagine we have a large corpus of T words. So for each position T, so this corpus can be described like that. For each position T equals to 1 to T, predict context words within a window of fixed size M, given center word Wj. So firstly, we traverse through all the words. Then for the next step, we choose a fixed size window, say 5 words on each side. So this M is 5. Our goal is to predict the next, our goal is to predict the 10 words surrounding the center word. By multiplying these predictions, we obtain our likelihood, representing how well our model predicts words in context. So this likelihood depends on our model's parameters denoted as theta here. So theta representing the parameters. So in this model, the only parameters are the vector representations assigned to the words. So here we can see that theta is all the variables to be optimized. So our goal is to minimize an objective function that represents our likelihood. So we adjust the original log likelihood function L of theta. We add a minus sign for minimizing instead of maximizing. And we include 1/t to compute the average goodness of predicting for each center word. We apply a logarithm to simplify calculations, turning a product into sums of log probabilities. So by using these 3 steps, we can design a better loss function for training our word model. So minimizing J of theta by adjusting word vectors representations enables accurate word predictions within context. So, but the next question is how to create a probability function for predicting a word in context based on the standard word. So that formula is shown here. How do we calculate this probability? Our model primarily relies on word vector representations, which are its only parameters. To simplify, we use 2 vectors for each word. One V when it's in the center. Sorry. When one V when it's in the center, predicting others, and another U when it's in the context. So each word has 2 vectors. And for each word type, we have these dual vectors. V for center and U for context. We then calculate the probability of a word O in context, given the center word C using this equation. So C is the center word and O is any word in context. We can use this formula to calculate it. So in the central part, the orange section in the denominator performs a dot product calculation. So this process involves multiplying components of our vectors together. So if different words share components with the same sign, like plus, or both of them are plus, or both of them are minus, in the same positions, the dot product will be large. Conversely, if they have different size, or one is large and the other is small, the dot product will be much smaller. So the orange part directly measures word similarity, indicating that words with similar vectors have similar meanings. So we keep explain this formula in details. There are 2 parts to this formula, P, O given C. The orange part uses dot products and the vector space for word similarity. And the rest involves passing it through a softmax distribution So this is kind of softmax function. The softmax function transforms numbers into a probability distribution, putting most mass where the maximum values are, but also spreading some probability mass elsewhere. So the blue part is used to normalize over entire vocabulary to give probability distribution. Yeah, so now we have a loss function with a probability model in place, like this. And our goal is to adjust our word vector representations effectively, enabling them to accurately predict the words that appear in the context of other words. So now let's focus on optimization. We are dealing with the vector components of various words, typically in high-dimensional space. Although for simplicity, we just show two-dimension picture here. Our aim is to minimize this function by adjusting the numbers in the word representations. We can have a metaphor. We essentially walk down through the slope of this space by following the gradient, ultimately finding better word representations when we are here. So in this case, we are optimizing a high-dimensional vector that contains all our model's parameters. So with the sole parameters being word representations. For instance, with a 100-dimensional word representations, d equals 100, we have 100 parameters for each word's context, and 100 parameters for each row as a center word. So if we have 100 words, we have 200 dimensions for the theta vector. So our aim is to optimize these parameters through the process. So here shows our objective function j of theta is actually the average negative log likelihood, like here. So our goal is to minimize object function which is equals to maximizing predictive accuracy. So here is our model. We aim to minimize it by adjusting these parameters, which are the contents of these vectors. To find the downhill direction in the space, we will calculate derivatives to determine the direction of improvement. So our goal is to move these word vectors downhill, optimizing the model. We'll analyze both parameters of the center word, which is denoted as VC, and also calculate the slope with respect to the UO vector. So like here, we say word2vec is an iterative algorithm that learns word vector representations to capture meaning. We move through a corpus focusing on a center word like into and predicting its surrounding words using a probability distribution. This distribution relies on the product of word vectors through the softmax function. Our goal is to adjust these vectors to improve the accuracy of probability predictions, favoring words commonly found in the context. So we work with two matrices, V for center words and U for context. So each word in our vocabulary corresponds to a row. Here, like word 4 is corresponding to U4 and V4. For example, if we have 6 words with 5-dimensional vectors each, this forms our outside matrix U. When computing for a specific center word, like word 4, we calculate dot product between V4 and each row of U. So we have to calculate 6 dot products, resulting in a vector of dot product scores here. Then we apply softmax to the result of this vector. So we are actually learning word vectors by minimizing a cost function. To do this, we calculate the gradient of the cost function with respect to our word vectors, theta. Taking steps in the negative gradient direction leads us downhill, aiming for the minimum in the space. So if we continue this process, we can finally reach the minimum. So here we can see that in essence, we calculate the gradient of the objective function with our current parameters. Then adjust these parameters by a small alpha. This is called our learning rate, to take small steps. This process is known as gradient descent. So this is the formula to update our parameter vector. So this is the matrix notation, meaning that theta is a matrix. While if we take a look at a single parameter, it looks like that. This is the current value, and this is the update amount. This is the learning rate, and we use these several values, we can get our new value of theta j dimension. So, but after introducing gradient descent, then we have a problem. What is the problem? The problem is j of theta is a function of all windows in the corpus. So how many are there of all windows in the corpus? Potentially billions. So this gradient is very expensive to compute. So how to deal with that? We have to find a better way. So the actual algorithm used here is called stochastic gradient descent, shorted as SGD. This is not gradient descent, because in gradient descent, J of theta involves the entire corpus. Imagine you need to process a few billion words to build a word-to-vec model. If you have to evaluate a billion center words and then 10 billion context words, this is under the condition a size window size of 5. It becomes computationally intensive. That results in calculating the gradient for such large data sets is incredibly slow. So since we are engineers, we don't allow slow computation. So we actually we usually take small samples of about 32 or 64. Larger samples are called mini batches, from which we estimate gradients. So using mini batches gives two benefits. The first is more accurate gradient estimates by averaging over multiple examples. So we have many 32 examples, or we have many 64 examples. This is called mini batches. And the second is faster computations on GPUs due to parallel processing, especially with batches of 32 or 64. This size just fits the hardware. So we may be curious about why there are two vectors, one for a word playing the role of the center word, one for a word playing the role of context words. Because this is used to simplify the math of partial derivatives. Using a single vector complicates this because the center word can also be the context. So as positions shift, a center word soon becomes a context word, and vice versa. So due to the symmetry of dot products, their vector representations are similar. So averaging these two vectors often provides the best single vector for a word. Okay, so now we are going to talk about what's the mechanism of picking samples from sentence and how to calculate each word vector. So there are two models proposed by the original word-to-vec paper, which is written by Thomas Mikolov. One of them is continuous bag of words, shorted as C-bar, and skip grams, shorted as SG. So in skip grams, one center word predicts context words, while in C-bar, context words predict the center word. So like word t minus 2 predicts word t. Word t minus 1 predicts word t. So we can know the difference between the real value of word t and the calculated value of word t. Then we can use it as the loss to update the network of this layer. So ideally, we sum over the entire vocabulary for probability estimates, but it's impractical and slow. So next, we are going to talk about how to evaluate word vectors. In NLP evaluations, we often distinguish between intrinsic and extrinsic evaluations. For tasks like word similarity or parse speech tagging, we use intrinsic evaluation to see how accurately the system performs, like grouping synonyms or tagging correctly. This method is quick and helps us comprehend the system better. So evaluation is very important. We use internal or intrinsic evaluation to see if a system is accurate. But to check if new techniques help in real uses like search or chatbots, we use other kind of evaluation called external. Sometimes new methods might not show improvement due to other reasons. Yeah, like the alignment of usage of the model. So the intrinsic evaluation method for word-to-vec is called analogy. We use a formula to find the word I as D and check if D matches the actual answer. So here, the analogy is like A versus B equals to C versus what? So what is I? So we will, from the whole vocabulary, we will find which word can get the highest value using this formula. And this word is D, is the D we are going to find. Yeah, so hopefully if the model is trained well, we will find queen as the word D. In the analogy of man versus woman equals to king versus what? So the author of Word-to-Vec, Thomas Mikolov, himself introduced analogy tasks and created a data set with many analogies. It tests relations like countries, capitals, and city-states. So here we can see that there are many city in state analogy, like Chicago is in Illinois, Houston versus Houston in Texas, Chicago in Illinois versus Philadelphia in Pennsylvania, Chicago in Illinois versus Phoenix in Arizona, something like that. So if you want to find more examples, you can visit this website. Here have many word vector analogies in syntactic relationship or semantic relationships. So another way is to compare the similarity calculation result with the result given by human. So here is a basic evaluation captures similarity judgment. So psychologists have studied human judgments of similarity for years. Annotators rate word pairs for similarity on 1 to 10 scale. So we can see that human annotators consider the similarity between tiger and the cat 7.35. Tiger and tiger, definitely 10. Book and paper, 7.46. Computer and the internet, 7.58. Plane and the car, 5.77. Professor and doctor, 66.62. So after collecting data and averaging human responses, like if we collect like 10 annotators for each pair, you can get rating like shown here. So we can also use cosine distance to calculate the similarity between words. So here if we have obtained each word to vec, we can use word to vec because it is the vector, so we can use it to calculate so-called cosine distance between two vectors. So for Sweden, we can find that Norway and Sweden in word-to-vec model, their cosine distance is 0.76, and Denmark is 0.71, and Finland is 0.62. So this table compares the model's similarity scores with human judgment. So we can see that the SG model here scores 62.8 on WS 353, 65.2 on the MC dataset, 69.7 on RG dataset, 58.1 on SCWS dataset, and 37.2 on RW dataset. So this shows the similarity between word-to-vec judgment and the human judgment. So we can see that SG model can get a not bad result compared to previous models such as SVD. Now we have learned the conceptual word-to-vec algorithm, but actually it still has some problem. So to be an engineer, NLP engineer, we must know how to avoid these problems and implement it. So let me introduce the actual word-to-vec algorithm. Okay. So this is our actual word algorithm. So we have two models. One is called one is called C-ball and one is called skip-gain. Let us use skip-gain as an example. So in skip-gain, our goal is to create a model that can predict words around a particular word. So when we focus on the word nut, the word taco is the one that is most likely to appear nearby. So this is the original conceptual skip-gain model. So to find the error, you can simplify. You can simply take the predicted vector produced by the model, subtract the actual target vector from it. So if we use 0 subtract model prediction 0.4, we get an error of minus 0.4. After obtaining the error, you can use it to adjust. After obtaining the error, you can use it to adjust or update the model's parameters. But when it comes the 3 layers model, when it comes to the 3-layer model, we have to tweak an incredibly large number of parameters. 10,000 times 300. 10,000 positions times 300 neurons. Plus another 300 times 10,000 neurons. This is simply not practical due to its sheer size. So how to deal with that? Instead of predicting one word next to another, we should switch our focus to figuring out if these two words are actually next to each other. So this is the original task. We input a word and try to predict its neighboring word. We reformulate this problem to be a test if these two words are neighbors. Okay, so we need to do other things to make this come true. Here is what we do. We rename the target word colon to be output word and introduce a new colon called target. So for each entry in the original target word colon, we set the corresponding target field into 1. So for nut and u, we put their target value to be 1. To nutshell, we put its target value as 1. So to create a binary classifier, we are all machine learning engineers. So we all know that we require not only positive examples, we also require examples where the outcome is negative. So here is how it works. For every input word, we pick random words from our list of words and label them with a value of 0. For instance, if our input word is not, we choose words like arrow and tackle at random and assign them a level of 0. So until now, we have transformed the skip-gram dataset into the binary target classification dataset from here to here. We also do some negative sampling for the words not appear in the dataset. So now we are going to training our model. At the beginning of training, we make two matrices. One called the embedding. One called the embedding matrix, and the other the context matrix. Each of these matrices contains an embedding for every word in our vocabulary. So the size of vocabulary determines one dimension. The other dimensions specify how long each embedding should be. A common value is 300. Though we saw an example of 50 earlier in the post. So this is usually 300, and this is the vocabulary size. And maybe I need to. To begin training, we set these matrices with random values. Then we kick off the training process. In each step of training, we work with one positive example and its related negative examples. So let's begin with our first set of examples here. So we have a positive example with its corresponding negative examples. Now we have 4 words. The word we start with, which is not, and the 3 other words are you, and the one we are interested in, arrow and tackle. These are just examples we are not interested in. To find the embeddings for these words, we check the embedding matrix for the starting word and the context matrix for the others. Even though both matrices contain embeddings for all words in our vocabulary. So you can see that each word has an entry in embedding and an entry in context. So we calculate the similarity by multiplying the input and output vectors, resulting in 0.2 for not and you. We can see that here. After applying the sigmoid function, we get 0.55. And then we subtracting it from the target value 1 because they are they are actually neighborhood. They are actually neighbor words. Give us an error of 0.45. These errors are used to update the model's parameters. So for not an error, we get an error of 0.25. And for nut and taco, we have an error of minus 0.68. All of these can be used to update model parameters. So now the training is done. We have made a small improvement to words like nut, you, arrow, and taco. Now we move on to the next step, doing the same thing. As we repeat this through our dataset, word representations get better and better. We can then stop training, discard context matrix, and use the embedding matrix for future tasks. So that's all. For more in-depth information, you can visit the official TensorFlow website here. And there you will find step-by-step instructions on how to train your own word-to-vec model. They even have code layer, so you can use like Colab-like coding or practicing to experience the training of word-to-vec. So that's all for today's class. Is any questions?
There are questions from the students?
I would like to ask a question. Sorry, can I ask a question through
Or
chat?
if you have questions, you can type in the chat room to save time.
Alright, thank you, Professor.
Oke, teman-teman bisa chat aja kalau ingin bertanya. Nanti bisa saya terjemahkan. Oke. Okay, to save the time, I would like to, excuse me. Okay. Wait a minute. Okay,
So the question is, what are the limitations that we should consider when using word-to-vec for word representations? I think this is a very good question. When using word representations, we must know that this performs good when for the words whose meaning is context independent. So for the words with multiple meanings, it performs not as good. So for example, like apple, it has two meanings. One is for two major meanings. One is for fruit, and like to eat apple, and one for the other. So since it has only one embedding in the learned model. So for this word, word vector cannot represent this their meaning better. So for this kind of words, we must have more advanced representation for them. that will be introduced next time. Okay, so the next question is, as far as I understand, word2vec is an algorithm to transform a text corpus into word vector to see the similarity of a word to another word. So can we train a two separate model for two languages and then see the similarities of them to use it for machine translation? Will this effective? I think this is a very good question. But the question will be how to map, how to construct the mapping between two word models. So usually we have a way to deal with that. We can prepare a corpus containing two languages, and we train a shared model that can be used to train a machine translation system. Because the word when we input a sequence of words, we can use a encoder decoder architecture to get the input of one language and translate into another language. But we share their embedding. Yeah, these two questions are both very good questions.
Okay, any question? It's a very good question, actually, indeed. Okay, anyone? We still have about 30 minutes. Still have plenty of time. I hope you can use this time well. Any question? No.
Although word2vec is not the best model at the current moment, but it is still essential to learn because it is very helpful for learning the follow-up models. So it is a breakthrough of natural language processing, which happened in 2013. So if you search papers, you can focus on papers after 2013, after the release of word2vec model. Because if you are a newcomer of natural language processing, you type any words, and in the internet, in the Google search engine or Google Scholar, you can find many papers, but you will lose your direction when you don't filter out some too old papers. So I suggest you just take a look at 2013 papers after 2013, especially papers after 2017, because 2017 is another turning point. In which year Transformers released, which we will introduce it next time. And after Transformer, we can grab the accurate meaning of the whole sentence, not just a word.
Okay. Any question? Okay, maybe I will ask to Prof. Sai. Okay. Will term weighting such as TF-IDF or PM25 be obsolete after the existence of word embeddings? Because we still have many applications that still use PM25 or TF-IDF, or it will be replaced with word embeddings in the future applications.
So, may I rephrase your question? You say that you are still using like BM25 or some methods or ways or scores or formula invented before, and how do we integrate this and the more embedding model? Is that right?
Probably yes.
Okay. I think they have, in my experience, both of them have some advantage. For like product name or names with very specific spelling, then BM25 is more effective. But for normal words, word2vec is more effective. So we can think about a model that integrates both advantages and then resulting in a better system.
Yeah. So PM25 will not be obsolete sooner. Okay, so. Okay, any question from the students? Okay. Okay, I just want to remind to all the students, okay, before we finish and before I forgot about it, please turn on the webcam as we will take screenshot for administrative purposes. So please turn on the screenshot, the webcam as we screenshot in its page. Okay, while you may think about question. Okay, wait a minute. Okay, first page. Okay, second page. Okay, 3, 2, 1. Okay, some students still have not turned on their webcam, so please turn on the webcam. There are still many students that still haven't turned on their webcam. Okay. Second page. Mohon nyalakan webcamnya teman-teman ya, meskipun sebentar saja. Okay. Page 3 ini banyak yang belum nyalakan webcam. Okay, the last page. Okay. Okay, thank you. Okay, any questions? We are still have about 15 minutes left. Okay, maybe I want to ask, maybe this is will be good for the student. In our case, there are many students that they have topics about sentiment analysis. So how do we use word embeddings in sentiment analysis?
Yeah, I think this is a very good question, and if we want to do sentiment analysis, like as we want to see if a sentence is positive or negative, the word embedding model can be used to calculate as the representation of a sentence. So the easiest way is to take average of word vector in each sentence. So we can use the average word vector, feed it into a classifier, and get the result of classification. Then we can construct a simple sentence analysis program. So we have a lot of training data of sentence and the label and the is corresponding label. We can use this data set to train a simple classifier that can provide a sentence sentiment of sentiment as positive or positive, neutral, or negative. Is that answer your question?
Yes, that's the simple way of to do it, one way of another. Okay. Okay. I hope it's also beneficial for the student. So we can use not only the FETF, which already obsolete, and also the M25, but we can also use word embeddings. For example, to be used in to be fit into LSTM or another classifier.
Yes.
Okay. We still have no other question from the student. Okay. Yes, from again, Mr. Moh Gustav Ali.
Yeah. So how do we use word to vec for neural machine translation? This is also a related question. Like the professor say, we can feed each word's word vector into a neural model like LSTM. We have encoder and decoder, so we can use that to train a neural machine translation model. Because there are a study which train word to vec on a multilingual corpus, they will find that words in different languages but have similar meaning, they are close to each other. Like the horse in English is very close to the horse in Spanish. Yeah, so we can just use a encoder decoder structure, which can be a LSTM or a transformer, that both of them are okay for building a neural machine translation system.
Is that good, Mr. Gustav? Mr. Gustav? Is that answer to your question? Okay. Yes.
Thank you. It's a
Hope
very
so.
good question.
Okay. 8 minutes left.
So, Professor, may I ask you how many languages are used in Indonesia?
Okay. Usually we are not only bilingual, but maybe trilingual. For example, Indonesian and also local language. Like in my case, it's Japanese, and also sometimes English. And we are also studying, since we are Muslim, we are also study Arabic.
Arabian.
Yes. So, but mostly in daily use, we are using maybe two, Indonesian and also Japanese. Maybe in some other places, they are using different language like Madurese or mungkin Sundanese. In Jakarta, they are using Sundanese. Maybe also mix code like English, Indonesian English. Sometimes this is also mixed code is being used in kind of accent in Jakarta Selatan, South Jakarta. They are using mixed code, and this is I can say this is popular now because they sometimes mix Indonesian and English word in one sentence, and this is one of challenge in NLP in Indonesia actually.
So, are all languages, do all languages have their own written form, or some languages do not have their written form?
Okay. Mostly they have written form, except for Arabic because we usually only read, not write. Even though we are reciting Quran, we only read it, but not write it.
So, do you have any plan in Indonesia to build a translation system between local languages and the official language?
Okay, actually, we have friends in Hong Kong. If you are interested, there are there is Indonesian. I forgot. Okay, there's a society or organization called INAJL. What is it, INAJL? This organization association focus in computational linguistic. Okay, INAJL is Indonesia Association of Computational Linguistic, and one of the PhD candidates, some of them are in Hong Kong right now. I don't know, in Hong Kong and also in Taiwan and Australia, and they are researching about Indonesian language, and also some kind of other local language, for example, like Madurese or Sundanese, and also Bukinese, and they are trying to reserve the local language because we know that Indonesia is a low research language. So we are trying to save and create the corpus for Indonesian and also for local language.
Yeah, I think that will create many that will create plentiful research opportunities.
Yes.
Yeah, because for building mainstream or rich resource language translation, I think academic do not have any opportunity to compete with companies like Google or Microsoft or OpenAI. We don't have that computational resource. So the only way to have our own stage is to focus on low resource.
One of the researchers that I know, which is a PhD student in Hong Kong, named Genta Winata. Have you ever heard it? There are Genta Winata and then Fajri Koto. As far as I know, they are also developing Indobird. Indobird is a bird for Indonesian language.
Indonesian bird?
Yes, Indobird.
Okay.
One of them is also my friend during my study in master degree from University of Indonesia. Indobird. They are also creating a crowdsourcing project named namely Nusa X or Nusa Crowd. Okay, there's Indolam. Okay, indolam.github.io, and there's a project called Indobird. I can share the link.
Yeah, very helpful. Thank you.
And also Nusa Crowd and Nusa X. Okay, it's called Nusa Indo NLP. And Nusa X. Okay.
Okay, thank you.
Okay, you're welcome.
I've once built a data set for Bahasa Raja. It was the work of one of my Indonesian students.
I see. May I know where he comes from?
Where I don't know which city. I cannot see. Yeah.
Okay. Maybe if you remember someday, you can tell us about him or about her. Okay. Because the time is up and we have to close this online session. We will have next session in next week with still Prof. Sai. Okay. Is it correct? What is the topic for next session for next week?
It's transformers.
Oh, transformer. Okay. Yes. And we still have 3 more sessions in this visiting professor and practitioner 3-in-1. Okay.
Okay. Thank you,
I think-
Professor.
I think that's all. I'm very grateful that we have Prof. Sai here. And I also want to thank to all the students for the participation. And this is a very invaluable insight on word embedding. Actually, I have several students that research in word embedding, but it was probably 3 years ago during the pandemic, and after that no one is interested in word embeddings. It's unfortunately. I hope after this session more students will like to know more about word embeddings. Okay, we hope that the student will gain knowledge from this session and will be beneficial in your respective fields. Until we meet again in next week session, stay safe and keep exploring. Thank you and goodbye. Thank you, Prof. Sai. Okay,
Goodbye.
bye-bye.
Bye-bye.
Okay.
Thank you, Prof.